So this week we're focusing on vectors, intuition, and operations. Our main topic: scalars, vectors, dot products. And today we are going to delve into the fascinating world of vectors. While are absolutely fundamental to understanding many AI and machine learning concepts. We'll start with the very basics, build a solution intuition, and then move on to some essential vector operations, focusing today on the dot products. So let's get started. Today's lesson will be light. It's not hard topic to discuss. So to begin, let's talk about scalars. A scalar is simply a single numerical value. Now, think of it as a quantity that represents magnitude or size. For example, temperature, your age, the distance between 2 points, or the time it takes to complete a task are all scalars. They are just single numbers that tell us how much of something there is. They don't tell us anything about directions. We can visualize a scalar on a number line where each point represents a specific value. Scalars are the simplest type of quantity in mathematics. They are just numbers that define how much of something exists, but they don't indicate any particular direction. Think of it like measuring the weight of an object. For example, 70 kilograms is just a number with no direction associated with it. Now let's move on to vectors. Unlike scalars, vectors have both magnitude and directions. Think of an arrow pointing in a scientific direction with a certain length. The length of the arrow represents the magnitude, and the direction it points represents the direction of the vector. Examples include velocity. While tells us how fast something is moving and in what direction, or force, which has both strength and direction. We can represent vectors graphically as arrow in a coordinate system, or algebraically as lists of numbers, which we can components. There are different ways to think about vectors. The physics perspective sees them as arrows, defined by their length and direction. Computer scientists view them as ordered lists of numbers, like coordinates, and mathematicians, they generalize, focusing on the operations of addition and scaling. We'll be focusing mainly on the visual arrow perspective. To visualize vectors, we use coordinate system in 2D. We have the x and y axis intersecting at the origin. Think of the origin as the center of our space. Vectors are arrows that start at the origin and point to a specific location. The coordinates of the vector tells us how to get from the origin to the tip of the arrow. Let's start with a familiar exercise from grade school. We'll plot a point 1, 2 on a XY number grid where X represents the horizontal direction and Y represents the vertical direction. We are already well on our way to defining a vector. The key difference is that instead of thinking of the world in terms of points on a grid, We will also need to start thinking about lines. We will plot a point 1, 2 on x, y number grid, where x represents the horizontal direction and y represents the vertical direction. We already well on our way to defining a vector. The key difference is that instead of thinking of the world in terms of points on a grid, we will also need to start thinking about lines. And a vector can be drawn as arrow from one point to another. This is what our example means moving 1 units right and 2 units up. The coordinates of vector act like instructions. The first number tells us how far to move along the x-axis, and the second tells us how far to move along the y-axis. We write these coordinates vertically in square brackets to distinguish them from points. Every vector has a unique set of coordinates, and every set of coordinates corresponds to unique vectors. Now let's talk about how we can actually do things with vectors. Just like we can add, subtract, or multiply numbers, we can perform operations on vectors. And of course, for subvector addition, we will use the tip to tail method. Imagine moving along one vector and then moving along the other. The resulting vector, the sum, represents the combined movement. Numerically, we add the corresponding components of the vectors. This concept is similar to moving along a number line. It's pretty straightforward if you have two vectors, and let's say A, B, and C, D, you add their corresponding components. So AB plus CD equals A plus C, B plus D, and of course, if you see an example, you just add the first number, 2 and 4 to get 6, and the second number, 3 and 1 to get 4. Imagine you have two vectors, like two arrows pointing in different directions. To add them, you essentially combine their effects. Think of it like walking a certain distance in one direction and then another distance in a different direction. Vector addition tells you the total distance and direction you traveled. Visually, you can think of it as placing the tail of one vector at the head of the other. The resulting vector, the sum, goes from the tail of the first vector to the head of the second. And let's really dig into scalar multiplication. It's a fundamental operation that helps us manipulate vectors in a very straightforward way. Essentially, scalar multiplication is about scaling vectors. Think of it like adjusting the volume on a speaker. You are making the signal stronger or weaker. In the case of vectors, you are adjusting their magnitude or length. When you multiply a vector by a number, a scalar, you are changing its length. If the scalar is greater than 1, you are stretching the vector out, making it longer. Imagine pulling on an elastic band. You are extending it. Numerically, scaling is super simple. If you want to stretch a vector by a factor of 2, you just multiply each of its components by 2. So, if your vector is 6y, multiplying it by 2 gives you 2x, 2y. It's just that straightforward. So, To summarize, scalar multiplication stretches or shrinks a vector, and it flips the directions when the scalar is negative. The operation is crucial for many applications, from graphics to physics, where we need to adjust the magnitude of vectors without changing their underlying directions, or sometimes to reverse it. Linear algebra is powerful because it allows us to translate between geometry and numbers. This helps data analysis visualize patterns and allows programmers to describe and manipulate space using numbers. Whether you think of vectors as arrows or lists, understanding these concepts is crucial for many applications, including AI and computer graphics. And of course, the dot product, for example, allows us to calculate how much one vector projects into another, and is used to find angles between vectors. It's a very important tool that we will cover in future sessions. The dot product measures similarity between two vectors. If the result is zero, the vector are at the 90 angle, perpendicular. This is useful in physics and AI. And all right, let's talk about the dot product a bit more. We've seen how it's calculated, but what's the big deal? One of the most useful things about the dot products is that it helps us find the angle between two vectors. Think of it, if you know the dot product of two vectors and you also know their length, you can actually calculate the angle between them. This is pretty powerful, but it gets even more interesting when we look at how it used in machine learning. In this field, we often want to know how similar two things are. And guess what? If we represent those two things as vectors, the dot product becomes a fantastic way to measure their similarity. Basically, the larger the dot product, the more similar the vectors are. This is used in all sorts of applications, like finding documents that are similar in meaning or recommending products that are similar to what you've bought before. So it's not just a math trick, it's a really practical tool in the world of AI. And so today we will explore the fundamental concept of vectors from multiple perspectives. We've seen how they connect geometry and numbers throughout additions and scalar multiplication. And in the next session, we'll build on this foundation by exploring linear combinations, span, and basis vectors. To reinforce what we've learned and to prepare for future sessions, your homework is to complete Unit 1 of the 3-1 Brown linear algebra series, which is titled Vectors. And of course, I'll share with you this link, Dot Products and Duality, short video which explains perfect all necessary you need to know about dot products. And super useful, you can find on Khan Academy Linear Algebra course, Unit 1, Vectors and Spaces, Lessons 5, Vector dot and cross product. This unit covers spaces, dot and cross products, matrices for solving systems, and known spaces. Completing this will give you a solid foundation for the linear algebra topic we will cover in the future. And of course, I highly recommend taking your time with the videos and pausing to really understanding the visual explanations. So today's topic, I told you at the start, is super light. So how the lesson not long, and I think that that brings us to the end of today's session. So thank you all for your participation. It was great to have you all here. If you have any questions at all, don't hesitate to reach out on our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. So if you want to review anything we cover, or if you know someone who couldn't make it today, you can rewatch it at your convenience. I really appreciate if you could take a few minutes to fill out the post-event feedback form. And of course, I'll share this video, and in comment I left homework, 3 short videos, which I highly recommend to watch you. So your feedback is invaluable in helping us improve and make future sessions even better. Once again, thank you for your joining. See you in our next sessions next Sunday. Until then, keep learning, experimenting, and building with AI.